So based on that simulation, let's talk about the properties of our sampling distribution of proportions. So in terms of what will be given in the problems, we'll be given some population proportion, or it could even be just a proportion that we expect to occur, and we'll be given some sample size that we're going to look at. Then with those two pieces, we can form the rest. So making our sampling distribution, the first thing we'll need to do is check the central limit theorem. So something that we just discussed in the simulation was how important sample size is in order to make sure that we have a bell-shaped curve, because that's where we want to end up here, is through these steps we want to end up with a bell-shaped curve that we can calculate things with. So to do that, the first thing we need to do is check the central limit theorem. And that's listed at the bottom here in this box. So the normal model is an appropriate approximation for a sampling distribution of proportions if the following conditions hold. So independence is that the individuals in the sample whose proportion we're finding must be independent of each other. So like rolling a die was independent, flipping a coin is independent, those probabilities aren't changing. Sampling people, typically if we have randomness, that'll imply independence a bit. Or what we can use is this fact that sampling less than 10% of the population. So if we're talking about like out of all Americans and we sample 100 people, that's less than 10% of the population, so we can assume independence. So what we want to do is make sure that we have independence in some form. Randomization, we should have randomness, and then also, if they don't specifically say it's random, sometimes we're just going to assume that it's random to move forward with the problem. So we should have some sort of randomness to the selection of our sample. And then the piece where we need to show work is with success-failure condition. And that's where we'll take our sample size times our population proportion and make sure that's more than or equal to 10. And then we'll also take our sample size times 1 minus that population proportion. So Q is just 1 minus P, and make sure that that's also more than or equal to 10. So they both have to be more than or equal to 10 for us to pass that success-failure condition. So then from there, what we're going to do is build our normal distribution. So building the normal distribution, what we need to know is what is the center and spread. So if we have this random variable, which in this case is representing a sample proportion, if we check the central limit theorem, then we know it's normally distributed. But then what we need to know is what is the mean and what is the standard deviation. So for the mean, what we talked about in the previous video was how this mean of our sample proportion, or this average of sample proportions, same thing, is just going to equal your population proportion. When we take these samples, they're going to center around that population proportion because that's what's expected for our samples. So for the center of this distribution, you're just going to use your population proportion. These pieces here, defining the mean and defining the standard deviation, you might see terminology that says define the parameters, and that's what we're doing here. The parameters is this population mean and population standard deviation. So to define the mean, you would just write in the population proportion. And then for standard deviation, I said there would be a formula for it, and it is right here. So the standard deviation of sample proportions. And you can write it either way with the population standard deviation symbol with the subscript of p hat works, or SD of p hat, same thing. What we'll be taking is this square root of p times q over n. So to get our standard deviation, we'll have this calculation to do of p times q over our sample size, all under the square root together. So with those two pieces, we'd have this distribution of samples so that if I need to find any information about a single sample that we take from sample size n, then we can talk about probability, or we could start doing percentiles. We use any of those tools that we did for the normal distribution. So let's see how this works in an example. Suppose 60% of all college students are either very satisfied or completely satisfied with their online shopping experience. You decide to take a nationwide random sample of 2,500 college students and ask if they agree. So this first question here, is it reasonable to use a normal model for the sampling distribution? So this idea of, is it appropriate to use a normal model? This is getting at, do we pass the central limit theorem? That's our test for whether or not we have a bell-shaped curve. So we need to think about three things. We need to think about independence, randomization, and success failure. So first, let's look through the pieces that we have here. So what they tell us is, suppose 60% of all college students are either very satisfied or completely satisfied. So 60% of all, they're giving us a population proportion. So there's our population proportion, 60%. Then the other piece that's going to be important to us is that they take a random sample of 2,500 college students. So that right there is our sample size. So it'll give us our population proportion and sample size. So independence, when it's going to be sampling people, the easiest way to think about it is that 10% condition. So 2,500 college students, that's less than 10% of all college students. I'm not going to ask you to write an explanation here, but that would be what I would write out. Really, I just want to know that you thought about, like, is there independence here? Are there answers influencing each other? Which, no, there isn't. So just write down independence with a little check mark to show you thought about it, and we're good to go. Randomization, we'll have that because they say it's a random sample, so we're all good there. And then success failure, this is where we'll show a little bit of work. So I'm going to take 2,500 times that population proportion of 0.6. I'm also going to take 2,500 times 1 minus 0.6, which is a 0.4. And what I should see is that both of those are at least 10. So the first one will be 1,500. That's more than or equal to 10, so we're good there. And then the other is 1,000, which that's also more than or equal to 10, so we're all good there. So we pass all three conditions for the central limit theorem. So is it reasonable to use a normal model? Yes, because we pass that central limit theorem. Again, as soon as one piece fails, then we can't do any of this. We would be stuck. So find the mean and standard deviation of the proportion of survey respondents who agree. So mean and standard deviation of the proportion. So that notation comes through mean of the proportion, standard deviation of the proportion. So mean of the proportion, there's no work to do here. All you have to do is copy down that population proportion, which was that 60%. And then we'll want to use the decimal form here in the calculations, so that'll be a 0.6. So with the mean of these distribution, I always just think like easy peasy, you're just copying. Standard deviation, however, has a calculation to do. So we want to use this square root of p times q over n. So what I need to do is take a big square root, and we're going to take 0.6 times q, which would be 0.4, over our sample size of 2,500. So put that in a calculator and we should get a 0.0098. So now with these pieces, we pass the central limit theorem. We know the mean, we know the standard deviation. We can start to think about our normal distribution. So we know it's normal from that first part there, and then now we know numbers to plug in because of the mean and standard deviation. So then we can start answering questions involving probability. So, what's the probability that the sample proportion of the 2,500 college students who agree is at least 57%? So, what we're doing here is we want to see what's the probability of having this value of p hat, or rather at least that value of p hat, given our sample size of 2,500, given that we expect this population proportion of 0.6 coming through. So now that we have our distribution set up, we have our mean, standard deviation. We should know what this bell-shaped curve looks like, and we can even go ahead and start to draw a picture before we go into any technology. We're going to have 0.6 in the middle. And then let's look at 2 standard deviations above and 2 standard deviations below. So that would be, I'm going to round here where we're using 0.0098. I'm going to go ahead and call that a 0.01, so 0.61, 0.62, and 0.59, 0.58. Okay, so this right here is our distribution of how sample proportion should behave. So our sample proportion out of 2,500 college students, so this is based on the sample size, and we want to find the probability that that proportion is at least 57%. So that means we're actually out here at 0.57, and we're looking for at least, so that's going to be the area to the right here. So it's going to be a big probability. We're going to be really close to 100% here, just based on this visual. So what we're looking for is under this distribution, what is the probability that x is more than or equal to 0.57? That's what we're interested in here. And if it helps, another way you can write this instead of x is really we're looking for a p hat. You could write this either way. It means the same thing, but it's kind of nice to see p hat in there because it is the sample proportion of 0.57. And what's this probability that that sample proportion is above 0.57 when we're expecting 0.6 to come out? And then with this sample size of 2,500, we have the standard deviation that we're working with. Okay, but from there, let's go ahead onto Stapplet. So we're going to our normal distribution. I want to calculate an area under the curve. Since we're looking for a probability, we have our mean of 0.6. Standard deviation, I don't want to round here. I'm going to keep that 0.0098. Plot that distribution. There's a more detailed graph there. And it's still 0.57. It's even beyond that third standard deviation away. So we're pretty far out there. And then we're looking for an area to the right because we're looking for at least 0.57. And let's go ahead and plug in 0.57 and see what we get out. So we are at 99.89%, so close to 100%. So that probability there is 0.9989 or 99.89%. Okay. Tricky thing here, because this just uses our normal distribution. The technology isn't really new, but how we're finding our distribution has changed. And another piece that's going to change is the sentence structure is a little trickier because we're juggling a lot of percentages here. So something to keep in mind with our values that we're getting out here, this 0.57, this is a sample proportion out of our sample size. Like that's some proportion out of 2,500 college students. That's what the 57% represents. Then over here, these values that we're getting out here is a probability. Or you could think of this as our percent chance. So when we go to answer the questions, we want to be careful about which percentage is going where. I just start with the percent chance just to kind of get it out of the way because that's really the answer we're looking for here. This whole question is what's the probability? So I would say there is a 99.89% chance that at least 57% of the 2,500 college students agree. So it's just a common thing I see come through here is mixing up these percentages, but this is our probability. This is our sample proportion that we're plugging in to see what the probability is. And the little extra number that comes through is the sample size, because in fact, this whole thing is based on that sample size there. So that's our process. Set up our distribution, get it into Stapplet, and plug in our numbers to get a probability out, and then make a nice sentence to go